I kindly welcome you to day 15 of Unit 7. Our homework is packet page 5 and 6, and today we'll work on some more practice with Taylor polynomials. Hopefully you've already turned in your bonus on Schoology if you are going to turn that in. So first one, we wanted square root of x centered at 1. So we've got to do out to the third derivative of square root of x, which I have there on the left. Sub in 1 for each of them. And we get our values of those derivatives, the 1, 1/2, negative 1/4, and 3/8. So the 1 goes over 0 factorial. The 1/2 over 1 factorial times x minus 1 to the first. Then the negative 1/4 over 2 factorial times x minus 1 to the second. We have x minus 1 because it's always x minus our center. And then you have a similar idea for the third derivative one. You could have just left it as that. That would be a full credit answer, or I neatened it up. So either of those last two lines would be full credit. In the second one, now we can't just use our Maclaurin for e to the x because we were not centered at 0. This one had us centered at e. But luckily our four derivatives are really simple. They're all e to the e when you sub them in. So you've got e to the e over 0 factorial, e to the over 1 factorial times x minus e to the first. And then keep going for each of the others out to the fourth. Either of those lines would be correct. I just neatened up the factorials in the second one, but you didn't necessarily have to. Natural log of x, we needed 4 derivatives because we wanted 4th degree. Sub in 1 for each of them because we wanted to be centered at 1. So you have 0 over 0 factorial plus 1 over 1 factorial times x minus 1 to the first. Negative 1 over 2 factorial times x minus 1 to the second, and so on for the others. Either of those lines would have been correct, either with the factorials or if you neatened it up. For 4, two ways you could do it. This one we were centered at 0. So there's your long way, doing out all the derivatives and subbing in 0. But try and be smart about it. E to the x centered at 0, we have our Maclaurin for that. It's 1 over 0 factorial, in other words, just 1. And then we have x over 1 factorial plus x squared over 2 factorial plus x cubed over 3 factorial. So that's for e to the x. We want e to the x squared, so just put in x squared for all the x's, and then stop when it gets to the 4th degree. So try and be smart anytime we have one centered at 0 if it's one of our ones that we have memorized. So in 5b, we want centered at 0 of x e to the x. So again, you could have done it the long way, done a bunch of product rules and everything, subbed in your zeros. Or over on the right here is the smart way. This is the way you want to do it. Write out your Maclaurin for e to the x. Then we just need to multiply by x to get x e to the x, and then cut it off at the 3rd degree. Next one, we were centered at 3, so we had to do it out the long way. Do 3 derivatives. Remember to do your chain rule. Or in other words, natural log is derivative of the inside over the inside. Once you have your 3 derivatives, sub in 3, you get 0, negative 1, and negative 2. So you had 0 over 0 factorial minus 1 over 1 factorial. X minus 3 this time because our center's at 3 raised to the first. And then similar idea for the second derivative and third derivative one. Either of those last two lines would be full credit. 5D, we're centered at 0. You could do it the long way, which I showed on the top there, or the smarter way to do it is starting here. Start with your Maclaurin for sine, then just multiply by x cubed, and we get this. Well, they want 3rd degree. Nothing is below the 3rd degree, so it would actually just be 0 for our 3rd degree polynomial. Tan, there's two ways you could do it. You could either do it with your derivatives, or you could do long division knowing that tan is sine over cos. I'll show you the long division way in a second. I think it's easier to just do the derivatives. So you had to do 3 derivatives. There was some product rule that you had to do there. Sub in 0 for each of them. So we'd have 0 over 0 factorial plus 1 over 1 factorial. It's just x because it's centered at 0. It's like x minus 0 raised to the first. Then you got similar ideas for the others. Either of those last two lines would be correct. If you did it the long division way, you would have to take your polynomial for sine, your Maclaurin polynomial for cos, and do long division with those and do it all the way out and just stop when you got to a cubed term. Okay, personally I think that is a little bit messier, but it's just your personal preference. All right, we want to do approximate square root of 10. So a nice square root close to that is 9. So we're going to do a Taylor polynomial for square root of x centered at 9. You could have reused your derivatives from the first question. Subbed in 9, we get each of our values of the derivatives at x equals 9. So we got 3 over 0 factorial, 1/6 over 1 factorial, x minus 9 to the first, minus 1 over 1 over 8, 2 factorial, x minus 9 to the second. Same idea for the third. Neaten that up. Then we want to approximate at 10. So P3 of 10, sub in 10 for all the x's, you get 3.1622 and change. They wanted us to compare it, and notice that is pretty close. It matches out to 4 decimal places. And 7, they gave us each of our values. So we didn't have to do the derivatives. We knew what each of those are going to be. We'll just put them over their factorials and then have the x plus 4's raised to the powers. That's where we get that first line there. So the top one, notice, is our second degree one. And then in A, the second one is the third degree. They wanted us to approximate at negative 4.2, so sub in for each of those. The one that's probably more accurate is the third degree one, because remember, add more terms, it is more accurate. So we're going to be in our notes packet, the day 15 lesson. So we've been saying these things a bunch, but it's good to just remind them because they're key ideas with Taylor polynomials. The Taylor polynomial matches the original function at its center. Same idea with all the derivatives. The derivatives of the Taylor polynomials match the derivatives of the original function at the center exactly. As you move away from the center, you lose accuracy. We can gain accuracy in our Taylor approximations by adding on terms. A good technique is to create new polynomials using ones we already know. So do substitutions, do operations, do derivatives, do integrals. All key ideas to keep in mind for these. So we want to test to see what you know. So see if you can write out 3 or 4 terms for each of these. So take a second, pause the video. See if you can test yourself without looking at any previous notes. And then hit play and we'll go over these quick to see how you did. So go ahead, pause now. So sine, remember, is an odd function. So we would want odd powers. So we would have x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus dot, dot, dot. Cosine is even, so we would want even powers. So we have 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus dot, dot, dot. E has all the powers, all the factorials, and is always positive. So we have 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus dot, 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 dot. Really, that 1 has a 0 factorial under it, which is 1. X has a 1 factorial over it, which is also 1. And 1 over 1 minus x, we want to recognize that that is really just our geometric infinite sum, where we have a first term of 1 and we're multiplying by x each time. So this is 1 plus x squared plus x cubed. So those are the biggest 3 ones. We'll see some others that would be good to memorize, but those 4 are the biggest ones to memorize. So let's say we've got some Taylor polynomial. It's centered at x equals 1, and it's the function that's shown there. What can we determine about our coefficients of our first three terms? Well, the first term, the coefficient deals with f of 1. Well, if you look at f of 1, that's the y value at x equals 1, it is positive. So we know that the first term is positive because the y value is positive at x equals 1. Well, the coefficient of the second term, it's got a factorial. 1 factorial is not really doing anything, but the coefficients would represent the first derivative. Well, our first derivative at x equals 1, we're increasing, so that second term should be positive because the slope is positive at x equals 1. And our third term, we've got the 2 factorial on the bottom, but in terms of signs, we can look and see what we know about our second derivative at x equals 1. Well, this is concave down, so we know our third term should be negative because we are concave down at x equals 1. So those coefficients can tell us information about what the graph should look like because those coefficients are really coming from our different derivatives. So say we've got a third degree Taylor polynomial here. And we want to know what information can we determine at x equals 7. Well, that first thing should be the value at x equals 7. So the first thing that we know, f of 7 has to equal 3. Well, the second coefficient, the negative 2, that should be equal to f prime of 7 over 1 factorial. Well, 1 factorial is just 1, so f prime of 7 should just be, oh, sorry, I take that back. That was, let's erase that for a second. Our second term, notice, is missing. There's no x to the first. So that means we know that f prime of 7 has to be 0. What would be our third term, our second degree term, coefficient's negative 2. So that means we know that f prime of 7 over 2 factorial must have to equal negative 2. Well, 2 factorial is 2, multiply it over, we get negative 4 is equal to f double prime of 7. So that's something we know about our second derivative. We can do a similar idea for the third derivative. 5 should equal the third derivative of 7 over 3 factorial. Well, 3 factorial is 6, so when we multiply that over, we get 30 is equal to our third derivative at 7. So we know f triple prime of 7 is equal to 30. Well, what do we know is happening in the function at x equals 7? Slope of the tangent line is 0. Second derivative is negative. If you have a negative second derivative, we're concave up. The only way you can be concave up and have a slope of 0, or sorry, second derivative is negative, so we're concave down. The only way we can have a concave down section with a slope of 0 is if you have a relative max. So what we would say is we would say, and the AP exam loves to ask things about this, we would say by the second derivative test. And just a reminder, second derivative test is you take the values where the first derivative is 0 and see their concavity at that point, and that tells you if you've got a relative max or relative min. So by the second derivative test, there is a relative max at x equals 7, since f prime of 7 equals 0, and f double prime of 7 is negative, so we'll say that is less than 0. They love to ask this on the AP exam. They love to put it on the no calculator section because we didn't need to know any information from our calculator. We're just making determinations by those coefficients in our Taylor polynomial. So let's look at an actual AP question. This is from 2005. So first we had to write a third degree Maclaurin polynomial. And this should say MAC. This is Maclaurin. There's a typo there. Now the information they give us, they tell us that we have a horizontal tangent line at x equals 0 and f of 0 is equal to 6. And then they give us an expression there that represents all of our derivatives at x equals 0 from the second derivative on. Well, if we want a third degree Maclaurin polynomial, we have to go all the way out to the third derivative. Well, they tell us in the question that f of 0 is 6. If there's a horizontal tangent at x equals 0, that means our first derivative at 0, 0. For our second derivative at 0, we've got to sub in 2 into our expression. So let's do the work here. So I have negative 1 raised to the third, so that's going to be negative 1 times 3 factorial over 5 squared, and then 2 minus 1 squared is just going to be 1. So this is going to be negative 6 on top and 25 on the bottom. For our third derivative at 0, we'll put in 3 for all the n's. Well, we're going to get negative 1 to the fourth now, which is 1. 3 plus 1 is 4, so we'll have 4 factorial. We'll have 5 to the third, and we'll have 3 minus 1 is 2, so we'll have 2 squared. So this is going to be 24 over 125 times 4. The 24 and 4 you can divide out, and that's going to give us 6 over 125. So we can now build out our third degree Maclaurin polynomial. Our original value was 6. First derivative is 0. So if you want, you can initially write it as, and if it's helpful, I guess I'll put a 0 factorial there just so you can see the pattern. We'll have 1 factorial, and we'll just have x. And I guess we don't need parentheses there. And it's x because it's really x minus 0. Then we'll have minus our second derivative over 2 factorial times x squared, plus our third derivative over 3 factorial times x cubed. And you could leave it like that. I'm just going to neaten it up. So this is really 6. Second term's gone. We'll have minus 3 25ths x squared. 3 factorial is really 6, so this will give us plus 1 over 125 x cubed. And then the follow-up, do we have a relative max, relative min, or neither at x equals 0? Well, first derivative was 0. Second derivative was negative. So this means we've got a concave down section with a slope of 0, so we should have a relative max. So how we would justify this, we're going to say, just like we did in the last one, by the second derivative test. There, or maybe we'll say f of x instead of there. F of x has a relative max at x equals 0, since f prime of 0 equals 0, and f double prime of 0 is less than 0. So they force you have to invoke the second derivative test on those, and the AP exam really likes asking ones like this. That's it for this video. Enjoy the rest of your day.